Hello, good evening, everyone. Welcome to our complex number system live class 2. So, I took you through complex numbers live class 1 in the first video. So, in this class, we are going to continue from where we reached. Please get set as we are going to explore the different subtopics under complex numbers. So to start with this tutorial class, I'm going to start with applications of De Moivre's theorem. So I'll take you through the different applications of De Moivre's theorem. So first of all, when we say De Moivre's theorem, what is it talking about? So in our first class, I made a note to you that if you have a complex number, say e to the power I theta, where I have r here, that is a complex number expressed in the polar form, raised to the power n is always equal to r to the power n multiplying I n theta. That is, whenever a complex number is expressed in the polar form and you want to find an exponent of that number, you simply find exponent of its real parts, but you multiply the n by its argument, as simple like that. So in a case where your complex number is expressed as r open brackets cosine of theta plus I sine of theta, everything to the power n, De Moivre's theorem is saying that this whole expression is simply equal to r to the power n open brackets cosine of n theta plus I sine n theta. So how is this theorem applied, or what's the usefulness of this theorem? So basically, we use this theorem first of all to find the nth root of unity. So the first application we are going to talk about in this class is nth root of unity. In complex numbers, we have 4 possible unity. When you talk about the unity, what you mean is that a complex number with modulus to be 1. So if you have a complex number with a modulus of 1, we term it as unity. For example, you have 1. 1 is a pure real complex number. That is, it's a complex number with 0 imaginary parts. You can have -1, also a pure real complex number. We can also have I, which is a pure imaginary complex number. Then finally, we can have -I. So these 4 are what we call unity, meaning they all have modulus of 1. That is why we termed unity. So what do we mean by nth root of unity? When I say nth root of unity, I mean that if you are being given a complex number where you are to find a powers of this, either this or that, then we can apply De Moivre's theorem to simply find the nth root of that particular complex number. Having mentioned this, let's take an example and see. So example 1. Let's take this. Find z cubed all is equal to 1. So find all the roots of this equation. So you know that this is a cubic equation, right? This is a cubic equation. Z cubed is equal to 1. But you know z is a complex number. So how do we find all the roots of this equation? This is where we apply De Moivre's theorem to solve such a problem. But before we solve this problem, let's see all the unity represented on the Argand diagram and their corresponding arguments. So considering 1, On the Argand diagram, I told you the imaginary part is represented on the y, while the real part is represented on the x, right? So if you are having 1, which is a real number, it's the same as having 1 unit on the real part. Therefore, our complex number lies parallel, and it also lies on the x-axis, right? And as you know, 8 modulus m is equal to 1. So what will the argument be? The argument of complex number 1 is simply equal to 0, because argument is simply the angle between a complex number and the positive x-axis. In our scenario, you can clearly see that the complex number 1 lies exactly on the x-axis, meaning that if two vectors, or if any two parameters you are considering are parallel, then the angle between them is 0. Therefore, the argument of the complex number 1 becomes 0 degrees. Now, let's see that of negative 1. Representing negative 1 on the Argand diagram, you have imaginary y here. Then since it's negative, you should have negative y, which is the negative imaginary axis. Here is x, which is positive real axis. Then you have negative x, which is negative real axis, right? So negative 1 will simply fall on the negative real axis here. So I'll place it here, negative 1. Our goal here is to find the argument theta, because we already know that 8 modulus is 1. So to find theta, what do? We need the angle from the positive x-axis to our complex number negative 1. That is z is equal to negative 1. So this is our complex number here, which is lying exactly on the negative x-axis, that is negative real axis on the Argand diagram. So looking at the angle from this side touching here, we can clearly see that it has an argument of what? Pi, right? So therefore, the argument for negative 1 is simply equal to pi. Let's see that for negative I. So when we consider negative I on the Argand diagram, negative I will surely fall on the imaginary axis, but on the negative side. So I have my negative imaginary axis and my positive real axis here. I'll simply put since it is negative I, it has a coefficient of 1. So it is 1 unit on the negative imaginary axis. So meaning I'll place, let's say, 1 somewhere here. So 1, negative 1 here. So I'll simply draw my complex number, which is negative I, like this, z equals negative I. I know that my m modulus of negative I is simply equal to what? 1. But what is theta? Before we do this, you know that when a complex number falls exactly on the real axis, theta is simply 0. When it falls on the positive imaginary axis, theta is simply equal to pi on 2, because it's 90. Something like this. It's 90. So theta becomes pi on 2. When it falls on the negative real axis, as we did for the negative 1, you can clearly see that our theta will simply be equal to pi. Is that not it? Now, once we come to this side, you get... So if a complex number is falling here, in the first class, I showed you the two conventions used to find the argument. The one which lies between negative pi less than or equal to theta less than or equal to pi. Then another which lies between 0 less than or equal to theta less than or equal to 2 pi. These are the two conventions. Any one you choose, you are going to arrive at the same answer. So taking the first part, which gives the principal argument, you realize that you are to measure argument from the positive x-axis, which is this axis. But you can do so in two ways. Either you move to the anti-clockwise direction, which has positive convention, or you move to the clockwise direction, which has negative. So moving from the positive x-axis on the clockwise direction to touch this gives us negative pi on 2 to be the argument of negative I. So you can clearly see that here. So now we know that you have 0 pi on 2 pi, negative pi on 2, then you come back to 0, right? So these are basically how we find the argument of our unity. So back to the question we were solving, I gave z cubed is equal to 1. How do we solve this? You want to find all the roots of this equation, which you term as a cubic equation. In complex number, when you see z, don't think that you are going to find z is equal to 1 to the power 1 out of 3, giving you 1. No. Whenever you see z cubed is equal to 1, meaning that you are going to get 3 roots. 3 roots. So this is an equation. So you are expecting 3 roots of this particular equation. So let's see. If you want to solve this problem, the first thing in the application of De Moivre's theorem is 1. You convert the complex number z to polar form. So always make sure that your complex number is turned into polar form before you can go ahead to apply the De Moivre's theorem. On that note, our complex number here is 1. To convert 1 to polar form, you need r, we need theta, right? R is simply equal to 1 since it is unity. Theta, as we drew on the Argand diagram, is 0 because the 1 will surely fall on the positive real axis. If it's falling, the angle between this and itself is 0. So 0 degrees. Whenever you are doing nth root of unity, please take note we deal with extended arguments. This is a new concept, extended argument. Extended argument means that when you are working with the plane, Cartesian plane, you can go several revolutions. So after 1 revolution, it gives 2 pi. After 2 revolutions, it gives 4 pi. After 3, it gives 6 pi. So in that order, so meaning extended argument is generally extending our argument or not limiting our argument to only 0, but rather 0 degrees plus 2 pi k, where k is the number of revolutions. Going round the complex plane doesn't change it. You only come to arrive at the same answer. That is why we use the extended argument to have repetitive but the same arguments in different form. So now let's see. I have r to be 1, I have theta to be what? 0. So the extended argument becomes 0 plus 2 pi k, meaning that my theta simply becomes 2 pi k, right? At this point, I'll have my complex number to be equal to z cubed to be equal to r1 multiplying e to the power I open bracket 2 pi k, right? So this is where I am. After getting this, so I got z cubed to be equal to e to the power I open bracket 2 pi k. And at this point, we need to find the roots of z, right? So we need to take these 3 we see here away. To do that, we take third root on both sides. So z cubed to the power 1 out of 3 is equal to e to the power I open brackets 2 pi k all to the power 1 out of 3. At this point, this cancels this, right? So z then becomes, at this point is where we are going to apply the De Moivre's theorem. If you have our complex number expressed in polar form and you are going to find exponent of that, De Moivre's theorem simply says multiply the power here by its argument and you are good to go. So here our complex number e turns e to the power I 2 pi on k everything over 3, right? So depending on the number of revolutions, we get all the root of z. Now, the value of k starts from 0, 1, 2, all to the power, all to the power here minus 1. So assuming you have a general thing like z to the power n is equal to 1, k will have the value 0, 1, 2 to n minus 1. So meaning that since you are finding the cube of z, we are expected to choose values of k starting from 0, 1, 2, but shouldn't be equal to 3, but less than 3. For that reason, in our problem, we will choose k to be equal to 0, 1, and 2 to get all the 3 values of our roots. So looking at the first root z1 is simply equal to when k is equal to 0. So in our case, when k is equal to 0, I'm going to get z1 to be equal to ei multiplying 2 pi 0 everything out of 3. Now 0 times everything here becomes 0, right? So z1 is simply equal to 1. Let's talk about z2. That's the second. z2 is when k is equal to 1. When k is equal to 1, you simply get e to the power I multiplying 2 pi multiplying 1. Everything out of what? 3. This gives me e to the power 2 pi on 3i. So z2 is simply equal to e to the power 2 pi on 3i. And we can represent this in the linear form as cosine of the expression 2 pi on 3 plus I sine the expression 2 pi on 3. You can further simplify this using your calculator. So when you punch this into the calculator, you tend to get the second root for our equation, right? So let's see. Here. So let's find z3. z3 is when k is equal to 0. Sorry, it's when k is equal to 2. Sorry. When k is 2, we are going to get e to the power I open bracket 2 pi times 2 all out of 3. And this is going to give me z to the e to the power I multiplying 4 pi on 3. So at this point, we simply get z3 to be equal to cosine of the expression 4 pi on 3 plus I sine the expression 4 pi on 3, giving me my third root. And that is how we find the root of unity. Root of unity. So we are done with our first question. Now let's see. Let's try another unity, then we move to different problems. So let's see example 2. Example 2. I have z to the power 4 is equal to negative I. Right? So find all the roots of this equation. Find the roots of this equation. To find the root of this equation, the first step is to convert our complex number to the polar form. You know that the modulus of our complex number is simply 1. What will be the argument? On the complex plane, negative I of 4 on the negative imaginary axis, so to 4 here, and here it becomes negative 1. And you know that the angle from the positive row axis to this side gives us what? Pi on 2. But moving on the clockwise side becomes negative pi on 2. So I have my theta to be equal to negative pi on 2. In our first question, I told you that we use extended argument to find all the roots of our equations. Our extended argument is done by adding 2 pi k to our arguments, where k is the number of revolutions you go. So in our case, our complex number z to the power 4 becomes 1, that is the r, multiplying e to the power I, then the theta will follow as what? Negative pi on 2 plus 2 pi k, right? So once you have this, then we can easily say that you are going to have z to the power 4 is equal to this whole expression, right? So I'll have e to the power I, open brackets, then I can simplify this expression. You can also choose to leave it. So let's make it 2 pi k minus pi on 2. So at this point, you apply the Morvis theorem by taking this 4 out. To remove this 4, I'll take the fourth power on both sides. So I'll get z to the power 4 all to the power 1 out of 4 should be equal to, open brackets, e to the power I multiplying 2 pi k minus pi on 2, everything to the power 1 out of 4. This simply cancels this, and we get our z to be equal to the expression e to the power I multiplying 2 pi k minus pi on 2, everything times 1 out of 4. So everything here divided by 4. Let's see how our simplification becomes. So z is equal to e to the power I multiplying we have 2 pi k minus pi on 2. 2 pi k minus pi on 2, everything multiplying 1 out of 4. So let's simplify this here. So my z is simply equal to, inside here you multiply 2 by this and I get 4 pi k. 4 pi k minus what? Pi all out of 2. This times what? 4. Is that not it? It simply equals to I, open brackets, 2 multiply 4 and I'll get 8. 4 pi k minus pi on everything over